Welcome everyone to the course. We are ready to start. Thanks for joining us today and appreciate all of you taking time to attend this course. We hope that you find information useful for your work. So my name is Julia Levitas. I am a product manager in our Tesla group here at NVIDIA and will help today with the class. So there will be a lot of material covered during the class, and we will post class recording on the course page. So by the end of the week, you will be able to review it one more time. As of now, we have posted the first lecture and also the first Q&A there as well. All the lines are muted, so please submit your questions through a Q&A pod on the right-hand side towards the bottom of the screen. While submitting questions, please make sure that you submit it to all panelists. That way we will be able to help. So all of us here will be answering your questions. We encourage you to use Q&A versus the chat window, so it's easier for us to monitor just one Q&A window. We'll do our best to answer as many questions as we can today. If you have any additional questions after the webinar, please send them to openacc@nvidia.com. Today we have two instructors helping out with the class. Matt Colgrove will be helping with a question in the background while Jeff Larkin is presenting the lecture. So Matt is a developer technology engineer at PGI, working on compilers and tools with a focus on customer support and OpenACC training. Jeff is a software engineer at NVIDIA's developer technology group, where he works on porting and optimizing HPC applications. He is closely involved with the development of both OpenACC and OpenMP specifications. So I'm sure you both of them are great instructors, and they're ready to share their knowledge with you today. So Jeff, I think we're ready to start.
Thanks, Julia. Welcome, everybody. This is lecture 2 in a 3-part series, so I encourage you to go back and watch last week's lecture if you missed it. I am this week going to be building off of where we stopped last week. So I am going to go ahead and assume that you've seen that lecture, and if not, please do go back and watch it so that you can kind of get caught up. Just a reminder for you that the objective of this course is that when all is said and done, we hope we've enabled you to accelerate your application that you care about using OpenACC. I really think it's one thing to be able to take simple application kernels, but we really hope that we can give you enough knowledge that you can take the code that you care about, the science that you care about, and begin accelerating. Here is the syllabus. So last week we talked about analyzing your code and parallelizing the code with OpenACC, and I'll revisit those 2 steps briefly. Today we're going to talk primarily about optimizations in the form of data optimization and also in the form of loop optimization. And the next week is just called Advanced OpenACC, and it's going to be kind of a mixture of topics that just don't fall neatly into either of these lectures, but that we feel important enough for you to see. Down at the bottom here, you'll notice the link. This is where you signed up for the webinar, and if you'll go back there, by the end of the week, we'll have both week 1, which is already there, and this lecture there available to you. Oops. So this week we'll talk about optimizations, and today's objective, we'd like for you to understand what OpenACC's data directives and data clauses are. How to manage data movement using OpenACC directly, because last week we relied upon a technology known as CUDA Unified Memory to basically ignore the device and host data and just assume that all data is visible everywhere. And that's not really a portable solution, so we want to go through and teach you how to use OpenACC to manage your data directly, and then that will make your code portable, and going into the future, it may even make your code run better as well. I'll also talk about how OpenACC identifies 3 different types of parallelism and explain to you this hierarchy of parallelism. I want you to be able to understand what's meant by loop decomposition and how to optimize that. And lastly, I've thrown in a few bonus optimizations that are so common, I want to make sure that you're aware of them so that if you encounter this in your code, that you'll know what to do. So we do have, we consider a 3-step process to accelerate OpenACC. Last week, we talked about analyze. We also talked about parallelize, and this week we'll talk about optimize. We did use an example code. In this case, it implements the conjugate gradient method. This code is available in our quick labs, and you'll be doing those this week. And I'll also make this code available online at a later time. So the first step we talked about to review was analyze. Analyzing your code involves getting a performance profile, and we used the PGProf tool to do that last week, and that helped us to identify what are the important functions within our code. In the case of this example code, there were 3 important functions, and helped us understand what are the loops within those functions that we need to concentrate on. We talked about reading compiler feedback. So the compiler does a good job of giving you messages to tell you what it sees in your code, what transformations and optimizations it does to your loops, how it is parallelizing your code or not parallelizing your code, and all of that information can really help you as you're accelerating your code to make your code better. And lastly, an important step is to understand your code, and really, once we've identified here are the important routines, to stare at them, read them, and understand what they're doing. And you'll see in a later slide here, as we're optimizing, that this understanding of the code sometimes is a key to further optimizing, because you know things about the code that the compiler might not. Now, after we analyzed, we talked about parallelizing, and parallelizing is the process of taking our loops, looking at all of the iterations of the loop and trying to make them run in parallel. And this could be running in parallel on a GPU, it could be running in parallel on a multi-core CPU, it could be simply be running in parallel using the parallel SSE or AVX instructions on your CPU. There's a lot of different forms of parallelism. We talked about how we would add the OpenACC directives around our important loops, and we talked specifically about the parallel loop directive, where the parallel directive generates parallelism that we're going to use in the form of lots and lots of OpenACC gangs, and then the loop directive, which took the iterations of our loop and distributed it to run in parallel across those gangs. We talked about how to enable OpenACC in the compiler. Here we were using the PGI compiler. This is available to you through our quick labs or through the OpenACC toolkit, and the link for that's at the bottom. But there are other OpenACC compilers available. And lastly, running the code on a parallel platform. And so I showed data from 2 different NVIDIA GPUs and also on a multi-core CPU. Now, we ended last week. We started with the serial code. I added OpenACC, and I ran it on 3 different platforms. One is a multi-core CPU. In this case, it was a fairly recent CPU. I ran it on a K80 GPU. Notice that while the GPU saw a speed up, it wasn't quite as large as the multi-core speed up. Now, part of this is because we're using only 1/2 of this board, and so that the performance in theory could be about twice as large. But part of that, as you'll see, has to do with applying some optimizations. And I also ran on a modern P100. You can see we saw a pretty large speed up there, and we're going to improve upon those this week. So let's talk about the optimize step. Now, the first step of optimizing is really to get a new performance profile to help us understand exactly how our code is executing. And we can actually use the same tool we were using last week, PGProf. It's able to do both CPU and GPU profiling. And there are other tools available. It turns out that the NVIDIA Visual Profiler and PGProf are roughly the same tool, so you can use either of those. But there are tools such as Tau, such as Alinea Forge, such as the Cray performance analysis tools, which can help you do this. Optimization frequently involves removing unnecessary data transfers to and from the GPU. Now, we ignored data transfer last week by using unified memory. This week, we're going to make it explicit, and so you can see what the process is like to remove data transfers. Optimization also involves giving the compiler more information about your loops. So the compiler is going to make its decisions about taking the loops and running them in a way that makes sense on, say, a GPU. But sometimes it doesn't have enough information, and by giving it more information, we can help it to do an even better job. And lastly, I do want to give you a few common refactoring techniques where code was written in one particular way, and it turns out that by changing the code very slightly, you can make a big difference in how parallel your code is. So step one here, we're going to talk about optimizing data movement. So instead of using UVM, we're going to manage our data ourselves. Now, if all you care about is running on this particular GPU or this particular compiler, you might argue this step is unnecessary. But OpenACC is designed to be portable. So really, we want to put these data directives in and explicitly manage our data. And that way, if we're running on a GPU, the data will be in the correct place. If we're running on a multi-core CPU, well, those data directives are probably ignored because the data is already there. Or if we happen to be running on a Pascal or beyond GPU where we have unified support for true unified memory, these data directives might help the compiler to fetch your data and pre-fetch your data to the device ahead of time and optimize things rather than waiting for the data to migrate on its own. So, there's a lot of good reasons to go ahead and put the data directives in, even though we ignored them last week. So the first step, if you'll recall last week, we built with this target accelerator flag, and I specifically said TA equals Tesla : managed, and that tells the compiler to use managed or unified memory. So I'm going to take that out and see what happens when I build. And right away, actually the compiler is going to abort. In one of our three big routines, in this case the matvec routine, the compiler actually can't build the code now because we're not using managed memory. So let's take a minute and look at these error messages, because these are the sorts of messages that you're going to encounter in your real code as you move it onto the device. First, this line up at the top in red simply tells you this is the generic compiler message that says something happened, I couldn't move this to accelerator, and it says see the minfo messages. Now, I always run with minfo, so I already have these here, but if you forgot the minfo flag, this is your reminder that there's more information there. Looking down, we see we're in the matvec function, and we get down to line 20, and it says accelerator restriction. So it's encountered something that it believes is not allowed to run on the accelerator. And specifically, it says these three arrays, A coefficients, calls, and X coefficients, the size of these are unknown. And since the compiler can't, at the time of compilation, determine the size of these arrays, it can't allocate space on the GPU and it can't move them to the GPU. So it's asking me for more information about these three arrays. And this last line at the bottom is just, again, a reminder that we got to the end of compilation, but there are some severe errors you need to address. So if you have a long build, you might see that and have to scroll up a little bit to find the actual error. But this message at line 20 is the key. The compiler aborts because it doesn't know the size of these arrays used inside a matvec. So let's look at matvec. Before we do that, actually, let me introduce to you how we're going to fix this. So OpenACC provides what are known as data clauses, and these clauses can be added to your parallel regions. They can be added to a region we haven't talked about called kernels, and they can be added to various data regions, which again we'll talk about in just a moment. And these inform the compiler information about my data and how the data is used. So I've listed on this slide the most common data directives, and we'll work through what they all mean. So copy in is the first one here. A copy in means for all of the arrays I have listed here, so you see list on all of these, for all of the arrays listed within the clause, I need you to create space on the GPU for this array, and I want to take whatever's on the host and initialize the GPU copy with that data. So this is a copy into the GPU or into the accelerator. Copy out does the reverse. Copy out says, I need this much space for these arrays. I don't care about the initial value, I only care about the final value. So at the end of this region, copy the data back to the CPU so that I can use it. Copy is a combination of the two, and so if you have to do copy data in at the beginning and back out at the end, you want to use a copy directive. And in fact, some people have tried saying copy in and copy out on the same variable, and some compilers don't actually accept that. So if you truly want to go initialize and then copy the data back, you want to use a copy clause. Now, create simply means I need space. I don't care about the initial value. I don't care about the final value. I just need space to work with. And so this is used for temporary variables. Delete is a special case I'll talk about in a moment, but is the reverse of a create. And lastly, there's one called present. And present is a promise that I'm making to the compiler that somewhere else that you can't see at this time, I have already taken care of the data for you. So I'm promising that to the compiler, so it's going to ignore any data movement questions for the arrays I've listed. But if I break that promise, I can expect that it's going to crash at runtime, so keep that in mind. So these are the clauses that we're going to add to our OpenACC to give the compiler more information about our arrays and how they're used. Now, I do need to make one further note on these clauses. All of them, when they're evaluated, will first check and see, do I already know about this array? And if I already know about this array, and I know this array is already on the GPU, I'm going to reuse the data that I already have on the GPU. If it's not already there, then I'm going to do the operation listed. So check and see if the data is present. If it's not, copy in. If it's not present, do a copy out. But if it is, it will reuse that. And keep that in mind, because this is if you did OpenACC programming a few years ago, this was not the default behavior then, and it is the default behavior now. And I think it actually really does help clean up the code, because now I can, at each function, I can specify here's exactly the data clauses needed for this for these loops. And then as I go back and optimize my data movement, as we'll see here in a moment, it will just reuse the data that exists. Now, the specific problem that the compiler is complaining about is it doesn't know the size of these arrays. So we need to provide something known as an array shape. So shape is slightly different than size. Shape does actually specify, okay, if I have multiple dimensions, it's the sizes of those dimensions and what the full array actually looks like. Now, sometimes, and this is the case with two of our functions, dot and waxby, the compiler can look at all of the loop iterations, and it knows how many iterations of the loop access that array, and it can figure out based on that, well, this is the size of the array. And so it knows, and it'll do the data movement for you. But sometimes the compiler can't figure this out, and when it can't, we need to give it shape. So if we look down here at the bottom, and I showed both the C and the Fortran versions because they are slightly different. I have a pragma ACC data. I'll explain that data directive in a moment. Copy in A. So I've said A, I want to create space on the device and copy the initial values. How much space do I need? Well, I'm going to start at 0 because C arrays start at 0, and I have n elements. And what's an element? Well, if this is an array of doubles, then it's going to be 64 doubles. If it's an array of floats, it'll be 64 floats. So it doesn't really care about your data type. It's just saying whatever that type is, start at 0 and do n elem of them. And this works a lot like a memcopy it does in C, and that's why it kind of has this syntax. Here's the starting point and how much data to copy. I will note that in both of these, you don't have to do the entire array. You can actually do a part of the array, which is what we're showing here with B. Fortran, the syntax is similar but slightly different, and this was done because just because it makes more sense in how the language is used. So we see a copy in of A, and now we've changed from square brackets to parentheses because this is Fortran, and we give the starting value and the ending value. So Fortran arrays don't have to start at 0 or at 1. They can start at any arbitrary number, and so we give the starting value, and then we give the ending value, and that's very similar to Fortran array syntax if you're familiar with that. And similarly, we can give a partial array using the copy out. So this is how we will provide the shape. So let's add these clauses to give shape to our arrays that the compiler is complaining about. So here's our code on the left. I've kind of moved the directives we had from bright green down to dark green to really focus on the bright green ones. And the three arrays that the compiler complained about are A coefficients, X coefficients, and calls. And those are actually used inside our J array where I have the three dots or the ellipsis there. So I've told the compiler, and I had to go look this up. A coefficients, now because it starts at 0, I've actually left the 0 off. Now you can just say colon. And how many elements are there? Well, the A structure has something contained within it that tells me how big it is, and it's this number of non-zeros. So this is the shape. I start at 0, and I copy number of non-zeros elements. X coefficients, this is our vector structure, and similarly, it has its own marker, and that is num rows. So start at 0 and copy num rows elements. And calls is another matrix, so again, it's the number of non-zeros. So I've given my arrays shape. Now the compiler understands how to treat these arrays, since it couldn't figure it out for itself. Now, I've also done the same thing with Y coefficients. I didn't have to. The compiler was able to figure out because it's used because of how it's used. So let's talk about why these three arrays were a problem, but Y coefficients wasn't. The three arrays that are a problem are only used, if I can get a pen, are only used within the J array here. Excuse me, the J loop here. Now, the one thing to notice about the J loop is the compiler actually has no way of knowing how many iterations this J loop is going to do. It knows it starts at row offset and it ends after row at row end. But it doesn't actually know the count. It doesn't actually understand at compile time how many iterations this does. So because of that, it can't determine the bounds of these arrays. If instead I look at Y coefficients that's used here within the I loop, well, the I loop can be easily counted. I start at 0 and I end at num rows. So the compiler understands the size of Y coefficients. Y coefficients starts at 0 and ends at num rows, and that's how much of the Y coefficients array that I need to move. So that's what we're seeing here. So that's why there's this difference of why Y coefficients doesn't matter. Now, I went ahead and put a directive in here because I happen to know that I don't need the initial values of Y coefficients. I only need the ending values. And so I went ahead and up the top here, right about there, I added my own copy out clause. And so now I'm telling the compiler, well, you don't need to copy this in, just copy it out for me. Now, the other reason that I like to be explicit at this level is now I have a fully functional loop nest here that I could isolate. If I wanted to, I could take this, I could separate it from the program and work on it separately and know that it works. And when I plug it back in, it will still work in place. And this is one reason that I really like to have the explicit data clauses here. Now, I'll note we didn't get complaints out of our other two routines, dot and Waxby. So I've ignored them. I'm not going back and adding the data clauses, although I could, and in doing so, I would gain that benefit again of being able to isolate the code for use in a standalone manner. So I build this now with these data directives in place. It's now capable of building. It's capable of running. It gives correct answers, but it actually gets fairly slow. And I probably should have put a slide here that showed the slowdown. But instead, I'm going to show you what pgprof shows us. So pgprof actually, can I draw a line here? Here's a pen. pgprof is actually showing us, so these green boxes, oh, that's awful color. These green boxes are actually showing us the kernel inside of MATVEC, and these tiny little slivers are our other two kernels. And the thing to notice is before each MATVEC, I've got a whole lot of copies of data into my MATVEC function, and at the end, I have a whole lot of copies back. I have some copies back out. So what's happening here is my code progresses, it calls MATVEC. MATVEC needs data, so it copies the data in, it returns results, so it copies the data back. And then it calls a dot, and again, dot needs some amount of data, so it copies it there, copies it back, and Waxby needs data, and it copies it there, copies it back. So this actually turns out to be fairly inefficient because we're constantly copying data back and forth when in fact we really would do better leaving the data in place. Now, we didn't so much encounter this last week because we were using unified memory. So as we started off with unified memory, we would put one function on there and we'd see too much data movement. And we'd add the next function up there and the data movement would decrease a little bit. And finally, by the time we added the third function, the data movement was completely gone because it was being fully used on the device. Here, now we need to go and take this and move our data movement to a higher level. So instead of at the beginning and end of each, I say each function here, in fact it's each OpenACC parallel region, the data needs to be copied back and forth just in case it's used by the CPU later on. The compiler doesn't know for sure whether your data will be used. All it knows is, I calculated the value of Y coefficients, so it must be important, so it will copy it back. We happen to know, again, because we analyze the code and we understand what it's doing, that we only really need the data back after we've converged upon an answer. And since this is conjugate gradient, the answer is the local minimum within that gradient. Once we've reached convergence, then we can copy the data back. So we need to give the compiler our understanding of how the data is actually used. So OpenACC has two different mechanisms to do this, and both of these accept those data clauses I discussed earlier. So keep that slide kind of in the back of your mind, and these will be adding these data clauses. First is structured data regions. So everything you've seen so far is very structured. A parallel region begins at the first curly brace and ends at the closing curly brace. Very structured. So I know my data begins there and it ends there. My execution begins there and ends there. Structured data regions work the same way. So I have a very defined beginning at the top here, which is my curly brace, and a very defined end here. And any data clauses I add to this data routine, this data region, applies within those curly braces. So you see here I have multiple parallel loops, and so if I said ACC data copy in A, then both of these parallel loops can use A without having to copy between them. So it takes the data movement and raises it up a level. And this is why it was significant earlier when I said the compiler checks first to see if the data is present on the device. So we get down here and the compiler knows at this point of the parallel region, or the parallel loop, that the data for A that I copied there is going to be there, and so I can reuse that. Now, if you're in Fortran, I know many of you are Fortran programmers, we have a slightly different format here. We'll declare here's the beginning of the data region and here's the end of the data region, and that's simply because until very recently Fortran did not have a block construct, and that OpenACC has not yet adapted to having that block construct. So you give the beginning and the ending point, and these must appear within the same subroutine or function. Now, one significant limitation to these is the fact that they do have to appear within some structured scope. So you could think of within one function in either C or Fortran. That's one way to view this. That within one function or one set of curly braces, one block of code, you must have the beginning and the end. C++ programmers came to us and said, hey, that's a significant problem for us because we frequently allocate our data inside a class constructor, and we deallocate it inside a class destructor. And so there's no structured place to put your data regions. And we thought about it and decided, well, the best solution for that is to kind of break up the beginning and the end of our data regions. And so you can have the beginning in one place and the end in another. And so after some work, we came up with the notion of unstructured data directives. And I've actually kind of warmed up to unstructured data directives to the point that I use them almost exclusively now. I really like certain aspects of having unstructured data regions. With an unstructured data region, you say, enter data. And what do I do when I enter the data? Well, maybe I copy in A, or I create B. I tell the compiler what to do on the device. At some later point in time, I need to take that back off the device, and so then I would say exit data. And what are the clauses for exit data? Well, copy out, because I may encounter that point, decide that I need the results back, and I'll copy it out before I take the array off the device. Or maybe I could throw the results away. In that case, we have a delete here, which is kind of the inverse of create. These allow me to move my enter data right up next to my call to malloc, or my call to allocate, and move my exit data right up next to my call to deallocate, or my call to free, or my call to delete in C++. To me, this makes the code much easier to maintain, because now when I come in later on, somebody new comes and is trying to learn the code, they see malloc A, ACC enter data A, and so they know, okay, I've allocated the space for A on the CPU, and if I have OpenACC, I've also put it on the accelerator. There's one additional clause I'll point out for exit data, and that is finalize. And this is fairly new. As a matter of fact, I'm not certain that it's even implemented in the PGI compiler yet. But the finalize tells the compiler, okay, when we reach this point, this is the absolute last time that I'm going to access this data. So no matter how many times I called enter data, you can stop here and take it off the device. So the default behavior is if I call enter data on A 4 times, I need to call exit data on A 4 times before it to come off the device. Finalize says, nope, I really mean it. I'm done with this. You can take it off. So that's what the finalize clause is. All right, so how do we apply these? Well, first, I mentioned C++ classes, and that was the motivating example. So let me show you how it's done here. But it's not limited to this use case. So I have a matrix class. The matrix class, if we look down the bottom, has 2 important data elements: the array pointer, which we call v, and the length, which we call len. So in the constructor, I record the len, and I allocate space in v. In this case, I'm allocating len doubles. And immediately after that, I say ACC enter data create, and I'm creating space for v on the device. Later on, I encounter the destructor. I'm about ready to delete this off the CPU. Right before that, I call an ACC exit data delete to tell the OpenACC, take it off the device, I'm done with it, and then it gets deleted from the CPU. It's really important, regardless of whether you're in C, C++, or Fortran, to do it in this order. Allocate on the CPU first, and then enter data, and then do the reverse at the end. Do an ACC exit data to remove it from the device, and then free it. If you don't, you'll, at best, leak memory, and at worst, cause a runtime crash. So we're not actually using C++ in our example, but it's just as useful, in my opinion, in Fortran and in C. And so here is an example of how we're using it in our conjugate gradient code. So the conjugate gradient code has a function called allocate 3D Poisson matrix, and this is where we actually allocate our matrices. And you can see at the top, if I put my pointer up here, we're calling malloc. I have a bunch of red mallocs here. That tells me the size of these 3 data elements: row offsets, columns, and coefficients. And then we actually have some work that initializes the code, so I'm going to go ahead and let those loops initialize the arrays. And then at the bottom, I have some enter data calls. Now, I'm performing a technique called deep copy. So what I'm going to do is I have A, and what is A? A is a matrix structure. The matrix structure contains the number of rows, the number of non-zeros, and then 3 arrays: row coefficients, columns, and coefficients. So I'm going to take that whole structure and I'm going to copy it up to the device. So that whole structure is up there, so now I can access the number of rows and access the number of non-zeros on the device. But if I tried to access those arrays, well, my pointers would still be pointing to host memory, and that would be a problem. So the next directive here fixes that, and the next directive says, okay, not only do I want A on the device, but I want the row offsets array, and here's the size of that. I want the columns array on the device, here's the size of that. And I want the coefficients array on the device, and I want the size of that. So this gives the compiler full understanding of this entire structure. So that's what we're doing here. The Fortran code, we do the same thing. It's very common in Fortran to have whole modules, and inside your module you may have an initialize function that kind of initializes all of the allocatable arrays and all of the data within your Fortran module, and another one that does the reverse. So it's a common pattern in all 3 of these programming languages, and so that's why I really like using these enter data directives. Since we entered, we do need to exit. So here's my free matrix routine or function here, and I'm just doing the reverse, and I do everything completely backwards. I take A row offsets, A calls, and A coefficients off the device. Now notice I didn't have to give size because I'm taking the whole thing off. So I'm taking those 3 off, then I'm removing the structure from the device, and lastly I'm freeing those on the host. So before you free the matrix, you have to remove it from the device, and then you can free on the host. Now I'm not going to show vector.h, but we need to do the same thing for our vector structure, and you'll see that in the lab that I'm going to encourage you to do this week. So you can assume I've now done the same thing with the vector class as well. On its initialize function, we allocate space, and its finalize function, we free. And I build it, and it builds fine, and I run it. And in this case, and I honestly really did make this mistake when I was first running through this lab, and I think some of you probably will as well. I started running, and I see on the left my expected results, and on the right, I notice, well, my numbers are no longer converging. So I should be constantly reducing the value. So I start off here at e to the +8, and I get down to e to the -5. So I should be converging. And here, my numbers are actually kind of all over the place. So this is not my expected result. So what happened was, I moved my matrix to the device, and I moved my vector to the device, but I missed one subtlety, and that was the fact that I had a function that initialized the values inside a vector, and I was calling that on the CPU, but those results were never getting reflected up to the GPU. So this is kind of an easy mistake to make, and so let me show you how to fix it. So after I've allocated space on the device, I need to have some way to force the compiler to refresh the data or update the data. So if I make changes on the CPU, I want to reflect that to the GPU, or vice versa. I've done a bunch of computation on the GPU, and I want to move it down to the CPU. And we do that using an update directive. And if you happen to be an experienced CUDA programmer, you can think of an update directive very much as a call to CUDA memcopy. It's going to try to either copy from one direction, from the device down to the host copy, or do the reverse. So here down at the bottom, you have an example here. So I'm doing some work on the GPU, and I want to give that result down to the CPU. Here I'm showing ACC update host. I'll talk about that host keyword in a second, but update host, take my copy of A, bring it down to the CPU. The CPU might write it to a file. It might do some other computation. It might do an MPI send. Then whatever I'm doing on the host completes, and I want to give the GPU back the freshest data, and so I would do an ACC update device. Now something to note here is that these directives only really make sense if your memory is actually distinct. like the case on these GPUs. If we were running on a machine where the host and the device use the same memory, then these directives will actually be ignored because there's already it's already there. So part of the power is that we can express to the compiler, here is how our data is used, and then the compiler is able to determine, okay, well, that means I need to do a memcopy, or that means I don't need to do anything at all. That's really very powerful because it'll allow your code to run anywhere. Now, I do feel like, and this is again putting on my hat as someone who represents the specification, I need to point out to you that the host keyword has actually been deprecated. And the reason for that is we allow you to take a parallel region and put it inside another parallel region and put it inside another parallel region. Now, in practicality, I don't think very many compilers actually support that sort of nesting at the moment, but it is allowed by the spec. And for that reason, we couldn't guarantee that when I'm actually running, that I'm actually updating the host copy. Instead, I'm saying, whoever encountered this update directive, update my copy. And so the word that was chosen to replace host is self. Now, you really can use them interchangeably. It's actually specified that they mean the same thing. But for kind of future-proofing your code, I do encourage you to get in the habit of typing self instead of host. Okay. So here is this function that I forgot about when I was running through the lab. It's initialize vector. You see it's a pretty simple loop that just loads a value into my coefficients array. And I say ACC update device. What am I updating? I'm updating v.coefficients. And how much of it am I updating? Well, I'm saying 0. The 0 is implied here, colon, n, and copy n elements. And similarly to the other data directives, in Fortran, you would say the starting value and the ending value for your update. So this was what was required to get correct results, and I do get correct results now that I've run this. So just a reminder, update device goes from CPU to GPU on our system, and update self or update host does the reverse. So now, if I rerun this code, you can see, and I'm here showing pgprof again, that the data movement has all been eliminated, and now all we see is all our kernel launches here, and the data movement is limited to just a few small slivers. Now I'm going to take a pause here because we're going to shift from data to directives. Just kind of glance over and see if there are any specific questions that I should answer to this. I do see someone asking questions in chat. Please ask questions in the Q&A pod so that they'll be addressed more quickly. Let's see. Those said that I may have had a typo on slide 15. Thank you for pointing that out to me. Is there a notion of memory per GPU, or is it always a common memory pool across all GPUs? And what happens if multiple GPU cards are used? Great question. So with OpenACC, each GPU you have has its own memory. And so we'll actually discuss in next week's lecture how to use multiple GPUs, but I'll discuss briefly that what happens is I will make a function call that says, use this particular device, use device 0 or use device 1, and until I tell the runtime otherwise, it will continue to use that device. And so I can say, use device 1, and call an ACC enter data of A, and now I have A on device 1, but not on device 0. And so each GPU is treated separately, and if you want to manage your data or your computation on multiple GPUs, you do have to do that explicitly. We're looking at ways we can make that more automatic. It's a pretty big challenge because the compiler needs to figure out what data is needed on each GPU. Should it be replicated on each GPU, or do they need their own, is there one global copy? So there's a lot of challenges there. But you are capable of using multiple GPUs, and they do each manage their own memory indirectly. There's a question, slide 17, I said copy out, I must have had a typo there that said that copy out allocates memory. Actually, copy out does allocate memory for the device. So when I'm at the beginning of my region, if I have ACC parallel loop, actually I'll go back to my slide that shows this. Here, so I have my ACC parallel loop, and notice there is a copy out of Y coefficients. Well, I still need space for Y coefficients on the device, and so copy out will allocate space on the device. It just won't initialize it with any data. It's just whatever garbage is in memory. I'll write to that space, and then it gets copied out. And yes, if this is the last time it's used, it will be deallocated as well. And I kind of left that deallocation part off the explanation. But in all of these cases, they do need to allocate space on the GPU and clean it back up. So thank you for asking me to clarify that. And I think, let me see if there's any others. If the compiler reuses data that exists on the GPU, it can cause trouble for the future. How can I erase the data that exists on the GPU before running the code? So the compiler, in this case, what I was referring to is the compiler sees that within this program, I have already put space for A on the device, and therefore it will reuse that same space for A. It's not that I'm reusing data from a previous run. I'm reusing data that I moved to the device earlier within this same allocation. So that's what I meant by that. And yes, you are correct that the data is not necessarily cleaned between two runs on the GPU. So it's but that's kind of outside of the scope of OpenACC. Is it a best practice to always provide shape information? Is there a way to know if the compiler failed to determine its shape and size? So I think it is definitely a good practice to go ahead and give the compiler as much information as possible. So I mentioned here that I went ahead, and even though the compiler didn't need Y coefficients, the shape of that, I already gave it to that. So that means if I go to another compiler, that other compiler, I'm not assuming that the other compiler is going to figure out the shape correctly for me. I've gone ahead and taken control to ensure that. So it is really a good practice. But to go to your second point, can you tell if a compiler has failed to determine the shape or size? And at least with the PGI compiler, this is the output message you would get. I don't have a copy of the message you would get from other compilers, but they would give you similar warnings. And it says right here, at line 20, the size of the GPU copy is not known. So that was the hint that you needed to say, okay, let me go look at what's happening at line 20 and give it more information about these arrays. Okay. What's the difference between, sorry, I have an error on my machine. What's the difference between Pragma ACC copy in versus Pragma ACC data copy in? And actually, there is not Pragma ACC copy in is not valid code. The copy in is a clause to something else. So you could say ACC data copy in. In this case, I'm only managing the data. I still remain on the CPU, but I'm doing my thread of execution remains on the CPU, but I'm handling the data movement, as opposed to ACC parallel copy in which case I'm copying into the device and then I immediately start running on the device. So that's how the clause is different depending on whether you're using it with a data or with, say, a parallel. Okay, I'm going to keep moving from there. Keep the questions coming, and I will revisit these. I want to make sure that we get through all of the material. So we've optimized the data movement, and truth be told, the data movement is the biggest optimization you will perform. So frequently what happens is I begin accelerating the code, I put some functions on the GPU, it slows down. I put some more functions on the GPU, and it slows down some more, and some more. And eventually, I reach a point where I've got enough things on the GPU that I need to take a stop and step back a little bit, and then optimize that data motion away. So if the first time you put ACC parallel loop on a loop, it slows down your code, don't panic. That's actually fairly normal because of this data movement that happens. But as you put more on the device and move your data movement to a higher level where you can share data between regions, that's when you begin to get a speed up. Once you reach the point where all of your data motion is happening explicitly, it's only happening when it's absolutely necessary, and again, your PGProf profile will look something like this, where we have lots of green and purple and blue bars, and very few of the tan bars, which would appear right here and right here. Then we can start looking at optimizing loops. Now, loop decomposition or loop mapping is how the compiler takes all of the iterations of my loop and determines how they will run in parallel on the GPU. So that's what that term means. If I say mapping, it's saying, okay, I've got 10,000 iterations, and I'm going to give 100 to this part of the GPU and 100 to this part of the GPU, and so on. That's one way of mapping it. Or it might map it and say, I've got 4 CPU cores, I'm going to send the first 250 iterations here and the next 250 iterations there. It will really look at how best to take the iterations I have and how they really map to the hardware. Compilers always give their best guess, but sometimes they just don't have enough information. So the default value with the PGI compiler is that you will generally find that they will create 128 GPU threads, or it'll be, say, a vector length of 128, and I'll discuss that term vector length in a moment. The Cray compiler, it may be 128 or maybe 256. I don't remember this point. I'm not sure the default in other compilers. So every compiler will make its default. We sometimes have to take the knowledge that we have of the application and tell the compiler, well, that was a good guess, but not good enough. And here's a better guess, and really give it some more information. So this, again, goes back to our earlier statement of understanding the code and what it's doing. So looking at my compiler feedback for MATVAC, which was that most time-consuming kernel by a significant margin, I can see it generated at line 16, which is, this is the feedback here, and line 16 at the top tells me, okay, that becomes my gang loop. And again, gangs are these big independent forms of parallel execution that we talked about last week, and I'll show you a picture in a moment. And at line 21, it encounters a different loop, line 21. And line 21 says, I generated a vector length of 128. So we already discussed the compiler doesn't know how many iterations there are here, so it had to choose something, and it chose its default value of 128. Okay, so that's what's going on here. It's chosen this value, but I need to look at my application knowledge and say, is that an appropriate value? And it turns out that in this code, the code doesn't actually even execute 128 times. See, if we go back to our code where this data structure is allocated, it turns out that the number of elements per row, which is determined here at line 16, is 27. So that loop iteration will execute exactly 27 times, and it's trying to execute it 128 times in parallel. So that's 101 extra loop iterations that are doing nothing. Now, I can see that because I understand the code. The compiler can't see that. And unfortunately, really, PGProf is not going to be much help here either, because it's just going to see, okay, yeah, these certain threads, well, they're executing really quickly because they have nothing to do. So there's not really a good hint to this, but by applying my domain knowledge, I recognize, okay, 128 is a poor value. 27 would be a much better value. So what if I reduce my vector length to something closer to 27? So let's take a moment and review what we talked about last week with vectors. So I showed you not quite this slide, but something else last week to talk about gangs. OpenACC generates these independent groups called parallel gangs. So here I have two gangs, one here and one here, and I was very purposely put a big space in between them because these gangs don't really talk to each other. They can see into the GPU's global memory, but they can't really talk to each other. They can't really collaborate with each other, and in fact, they essentially don't know the other gangs exist. Now, we also talked about vectors. And to remind you of what we said last week, a vector is essentially some number of elements that execute together. In hardware, they might actually execute one instruction simultaneously, or the hardware may just say, we'll execute one instruction and it will move through all of the data elements before it executes the instruction. There's various ways to implement vectorization, but you can think of it as, in this case, we have 8 boxes that operate together. So all 8 of those boxes will be executing one instruction. Now, what I didn't tell you last week is that OpenACC has a level kind of in between that, and that's called workers. So here in these cartoons, I have 3 workers per gang, and the gangs will always have the same number of workers, and the workers will always have the same vector length. So let me give you a really tangible example of what gangs, workers, and vectors mean. So let's say I have an office building, and I want to get every room in the office building painted quickly. So I hire a painting company, and they come in, and they need to figure out what's an efficient way to paint this building. So chances are what's going to happen is they'll bring in a whole bunch of painters, and they'll organize those painters and say, all right, this group of painters is going to paint the bottom floor. The next group of painters is going to paint the next floor, and another group is going to paint the floor above that. And as you complete your floor, go to the next floor that is free. Okay, these groups of painters are our gangs. The gangs kind of work together. They're on the same floor, so they can communicate pretty well with each other. I can look at one of the other painters and say, I'm going to paint this wall, so stay out of my way, and I'll stay out of your way on that wall. It's pretty easy for these painters to communicate with each other. But for the different groups on different floors, it's kind of a pain for them to talk to each other. It's really hard to synchronize. It works better if they just operate independently of each other and ignore that the other ones exist. So that's my gangs, that's my workers. The vector is, if you can imagine, every painter has a paint roller. How much wall can I cover in one stroke? Well, that will be determined by how big my paint roller is. If I have a 4-inch paint roller, it's going to take a lot of strokes, but I'll get the wall done. If I've got an 18-inch paint roller, I'm going to be able to cover a lot more space. This is my vector length. How much of the wall can I cover with one stroke of my roller? This is the same as our 3 levels of parallelism. Vector length is the width of work that's happening at one time, in this case, the stroke of a roller. The number of workers is how many painters we have that are working together on the same floor that can easily communicate and synchronize with each other. And then the gangs are the different groups of painters operating on different floors. That's how our 3 levels of parallelism work. Now, most of the time when you're starting off with OpenACC, most of us will ignore the worker parallelism. It's usually sufficient to just concentrate on gang and vector. This code, I chose this code not by accident. I really wanted to demonstrate for you the times when you might want worker parallelism as well. So how do I now understand what my 3 levels of parallelism are. How do I use that? How do I give the OpenACC guidance based on that? Well, it turns out there are clauses to my loop directive that do this. So gang, worker, and vector clauses can each be added to a loop, and to tell the compiler, take this loop, and here's the type of parallelism I want you to use. Now, most compilers, actually all the compilers that I'm aware of, your outermost loop will be a gang loop, your innermost loop will be a vector loop, and the other loops will be used, may or may not be used how it sees fit. So we can give some additional information by using gang, worker, and vector. In addition to that, we can tell the compiler how many gangs I want, or how many workers I want within each gang, or the vector length or the roller size of those workers. That's using these clauses: num gangs, num workers, and vector length. So here's how it's used down below: ACC parallel loop. And I'm telling the compiler, this outer loop, I want you to make it a gang loop, and this inner loop, I want you to make it a vector loop. And again, that's kind of would most likely be the default behavior here. More interesting, in my opinion, is what if I want to have multiple levels of parallelism on the same loop? So here's an example. I have a loop vector on the inside. I'm reducing the vector length to 32, and I also want to get some worker parallelism out of my outer loop. Now, why would I do this? Well, I might do this if the inner loop has very short execution. Maybe it only executes 20 times. That's not really a good number for vectorizing. So maybe I would take some parallelism out of the outer loop. And if I wanted to do this manually, if I want to do this myself, I would have to kind of break up my loop, restructure it so that I have an outer loop across kind of blocks of work and an inner loop that works within those blocks. By applying multiple clauses here, in this case gang and worker, I've just told the compiler to do that for me. So I don't have to do the error-prone process of making sure I find every little edge case in trying to break up my loop and to use different levels of parallelism. Compiler handles it for me. And that's a really, really useful feature. And so keep in mind that the compiler can do that for you. Okay, so let's apply this to our code. And once again, I tried to kind of darken the green of the directives you've seen and brighten the green of the directives you haven't. I'm going to tell the compiler, first, at line 20, make sure you vectorize this. Now, the compiler is, in this case, doing that by default, but I'm just kind of forcing the compiler to do that. Make sure this is vector, and use a vector length of 32. Now, why did I choose 32? I told you that 27 is the optimal number, and I chose 32. On NVIDIA hardware, our code executes on units that we call warps. And warps, it turns out, it's actually a weaving term. So if you want to go back and look up, it comes out of weaving. But it's an execution unit on the GPU. And for all GPUs we've ever built, it's 32. Now, we make no guarantees it will always be 32, but it always has been 32. And so on NVIDIA GPUs, your vector length really needs to be a multiple of 32. If I did 27, the compiler would possibly round it up to 32 for me, or it might complain and say, sorry, that's not a valid number, use at least 32. That's why I've chosen 32 here. So we'll still have 5 threads doing nothing, but that's a lot better than 101 threads doing nothing. All right, where am I? So I'm going to build the code and run it, and in this case, actually, let me jump down to those results, if I have them. You can see I actually do get a performance improvement of about 40% by doing that, but we want better. So now that I've applied all of my domain knowledge, I'm going to start using my tools. And so here's pgprof, and I'm going to zoom in here, so sorry if it seems small at first. It tells me that matvec is the performance limiter. I've used something known as the guided analysis tool, which is just kind of a wizard that guides me to this point. So I'm going to click this button here in a moment. But first, let me zoom in on what it's telling me here. This graph is telling me that the kernel performance is limited by latencies. Specifically, it says instruction and memory latency. So this is telling me that there's times when my threads are sitting idle, waiting for either memory to return or my instructions to be ready to execute. Now, if you'll recall back to last week, GPUs are built to tolerate latency. And how do they do that? They do that with parallelism. So when I see here that my code is limited by instruction and memory latency, that is a hint that I don't have enough parallelism. Specifically in this case, if you know anything about GPU hardware, and I've tried to avoid going into too many GPU details in this course, keep everything at a high level, but GPUs are organized into units called streaming multiprocessors. These are similar to CPU cores in that they're just kind of independent parts of the GPU. And GPUs can have one, or GPUs can have lots. And depending on which GPU you buy, the more expensive GPUs have more SMs, streaming multiprocessors, because that allows them to do more work. Or the least expensive ones you might get in a mobile board might have one. And that's so each of those units can run some number of threads. And specifically, we want to make sure there's enough parallelism per each one of those streaming multiprocessors to keep it busy. So let's go back and get the tool to help us figure out why they're not busy. So I click on here this Perform Latency Analysis button. The guided analysis tool has kind of led me to this point. I do that. It's going to lead me to a graph. The screen here that is its latency analysis, and really it brings me down to a graph on occupancy. So let me explain what occupancy is. GPUs report a measure of occupancy as how good a job I'm doing keeping my resources busy. So again, we have some number of SMs, streaming multiprocessors. We may have 1, we may have 30, we may have any number in between. We may have more on some processors. Within a streaming multiprocessor, there's certain shared resources that dictate how much parallelism can run on that processor. There's a small amount of memory that we refer to as shared memory. If you use up all the shared memory, you can't put more threads on there. There's register space. So every thread uses some number of registers. If I use too many registers, I can't run more threads. So there's all of these different shared resources that dictate how many threads are actually able to run. If I'm able to kind of peak the hardware, peak the streaming multiprocessor with the maximum number of threads it can run, which on this particular GPU is 2048, then I get 100% occupancy. If I'm only running 1024, then I have 50% occupancy, and I should figure out why. Now, 100% occupancy does not guarantee best possible performance. There are lots of codes that perform well with 50 or 60% occupancy, but it is a good thing to strive for. So let's try to find out what's going on. So zooming in a little bit on this graph, I see that my current occupancy is 25%. So I'm using a quarter of my resources on each of these streaming multiprocessors. Okay, so why? Why am I only using 25% of the resources? Just as a note here, I didn't circle it, but that 25% comes from knowing 2048 is the maximum number this streaming multiprocessor can run, and only 512 are actually there. This does not guarantee that all of them are running simultaneously, but this means that this is how many are available to run on the multiprocessor. Okay, so I'm at 25%. Well, what I see down here is there's a big red row, and the color might not come through well on the WebEx, but this row turns out red on PGProf, and it tells me, okay, if I want to get to 2048 threads, given the current size of my thread block, I would need 64 thread blocks to do that. Okay. How did it get that number? Well, what's my thread block size? My thread block size is 32. 2048 divided by 32 is 64. Now, this other column to the right is telling me the maximum number of thread blocks that actually can be managed by my streaming multiprocessor, and that's 16. So I would need 4 times as many thread blocks, 4 times more thread blocks than this can hold. Okay, so why is that? Well, the reason for that is I don't have enough threads in my thread block. So I mentioned this term warp, which is 32 threads, and we see here I have 1 warp, or 32 threads per thread block. So again, we've reduced our vector length down to 32, and while that's helped us in that we're not executing 101 loop iterations that do nothing, it's actually hurt us in that now we're not fully utilizing our our GPU resources. We need at least 4 times as much parallelism as is available on that loop. This is where worker parallelism comes in. When you have these small innermost loops, small inner loops that just don't have enough parallelism to saturate the GPU. And in those cases, if there's not enough parallelism there, then we need to increase the size of our gangs by taking parallelism from another loop in the form of workers. And that's what we'll do here. So this is why I really like to use this code. It forces you to understand this is the situation where workers can be used, when there's not enough vector parallelism and we need to find parallelism somewhere else. So let's apply this to our code. We have here on the right, we kept our vector loop. We now take the top loop and we say, make this loop both gang and worker. How many workers? 4. And how many gangs? Well, I'll let the compiler figure that out. I never, ever adjust num gangs. I always let the compiler figure that out. But num workers 4, and so now I've increased my parallelism by a factor of 4. So the compiler will break up the outer loop for me. It will run 4 workers per loop times 32 vectors. That's 128 threads per thread block. If I rebuild, rerun, and look at the output, I can see down the bottom that the compiler did honor this. If you happen to have a background in CUDA, you can see that it actually gave me some additional information about how this maps to CUDA. That's maybe useful for you. And if I run it, I now see I get about a 2.5 performance increase above where I already was, or a little over 3 performance from the original. So this all came from just taking the iterations of my loops and figuring out how better to map them to the hardware. And since last week I showed you several different versions, here again is the original serial code. Here's the multi-core code, a little over 5x performance. The K80, 1/2 of a K80 board is roughly equivalent to the full socket of multi-core, and then the P100 here is about a 20x performance improvement, or about 3.5 to 4x the multi-core socket. Okay, this is all running the same code, simply changing my compiler flag to move between these three versions. Now, I made that optimization for my GPU. That might not be a valid optimization for all devices everywhere. So I don't want to teach you these optimization clauses without teaching you one further one, which is device type. And device type is used to say, these optimizations I'm telling you, only apply them to NVIDIA, or only apply them to Radeon, or whatever target you're working on. And that way, when I encounter a new machine that I've never seen before, I don't want to make a bad decision for that machine. So device type is a clause. Here you see I say device type NVIDIA, and any clause after that, up until the next device type, affects NVIDIA. So here I'm saying, okay, for NVIDIA devices, I want a vector length of 256. For Radeon devices, and I just made up these numbers, I might want a vector length of 512. So this allows you to specialize here. Any other device I run on, multi-core, ARM, Power, FPGA, whatever other platform I might run on down the line, the compiler will choose the default value for me. Okay, so we're running up against the time, and I want to leave a little bit of time for questions. So I'm actually going to skip some of these common optimizations for now and revisit them next week. And close by once again showing you our quick labs system. This week, if you did not take any labs last week, I kind of left them as kind of an optional. If you want to, this week I'm really encouraging you to do the labs. Go to this page. This is developer.nvidia.com/quicklabs sign up. This is going to be these slides are provided so that you can you don't need to write that down right now. Sign up and enter the promo code OpenACC16, and this will give you enough credits in our Quick Lab system to do all of our OpenACC labs. Please note, it does take some amount of time from the time you sign up until you get the letter kind of confirming your account. Sometimes that could take up to an hour or so. So keep in mind if you don't get an immediate confirmation that it is coming, and you'll get free credits. And specifically this week, I want to encourage you to go there, and if you have not already taken the 2x of 4 steps, it's a great introduction, but I want to encourage you to take profiling and parallelizing with OpenACC, and also expressing data movement and optimizing with OpenACC. And the reason I encourage you to take these 2 labs is this is the code that we've worked on for the last 2 weeks. So you've already seen the answers, and now you can go and experience it yourself and understand, okay, what if I type this? What happens? If I type this other thing, what happens? And understand what the compiler does with your code. As a reminder, in addition to our Quick Lab system, you can go and get a free OpenACC compiler from us at the OpenACC Toolkit website. If you happen to be affiliated with a university in some way, you're a student or a professor, it is completely free. If you are not, you will receive a 90-day trial. There is an OpenACC book that just became available this week, and go check this out. It's available. I do know for a fact it's available from Amazon. And I do also want to point out that we are going to take, after these live lectures are done, we are going to put up a bit of a quiz at the end, just to kind of demonstrate that you did listen, you paid attention, you did the labs, and then we'll not only if you are a college student, we'll send that to your professor if you would like, but also it will enter you a chance to win a free GPU and a free book. For more information, I encourage you to go check out these sources. And I'll leave this up as I begin to address questions here. Please, please, please go watch the recording of last week if you have not already. And also, if you have any questions, please go to Stack Overflow. All right, so I'm going to move over here to the questions pod. Please be sending your questions in, and either Matt or I will be answering them. Are there any IDEs with knowledge of OpenACC integrated, like syntax completion, things like that? I'm actually not aware of any that do syntax completion on OpenACC. Obviously, they will recognize that these are compiler pragmas and highlight them as such, or in Fortran, they will highlight them as comments, but I'm not aware of any IDEs that actually interpret the OpenACC syntax and do completion. If you find out about one, please email us at openacc@nvidia.com and let us know, but I'm not aware of any. Are there any OpenACC implementations or frameworks for Java? No. OpenACC supports C, C++, and Fortran. The only key in I can give you for other languages is any language that can bind into C or C++ or Fortran could call into those functions. And so I've heard of people that want to try to do this with Python, for instance, but no, there are no implementations for Java. And I actually see an IM from a live participant who happens to know me that says there is a plugin for Eclipse that does this. Can you please post that to the chat, and we'll make sure that gets put out there. Will Intel ever have OpenACC support? We compare and evaluate, and should OpenACC versus OpenMP and OpenCL. Intel has not announced any plans for support for OpenACC. Obviously, cannot speak for them. The Intel compiler supports OpenMP. How should you compare OpenACC and OpenMP? In my opinion, the way to compare them is on a measure of productivity. If you go back to the GPU Technology Conference from this year, gputechconf.com, I did a talk along with a coworker. He and I both serve on the OpenMP and OpenACC committees, and we tried to be as fair as possible, comparing the benefits of each of those and the trade-offs. But no, the Intel compiler does not support, and I don't know of any knowledge. But I do have, as Matt pointed out, there's some videos available. Here's an interesting question here. Does OpenACC automatically parallelize over GPU and CPU at the same time, or must we choose at runtime? Currently, OpenACC has no mechanism to split across different types of devices or multiple devices in general. So if you think about a multi-core CPU, you can consider that as a device with multiple parallel cores. You consider a GPU a device, and there's currently no way to divide your work across both. The load balancing and particularly the data management is a bit of a nightmare. We are absolutely looking into that. There's been some research done, people demonstrating how it might be done, but within a specification, it's a big challenge, and we have not addressed that at this time. First, must we clear pointers from the GPU and then from the CPU? And by clear, I'm going to interpret that as freeing them. You can certainly clear the data if you like and zero the data out in both places. But in terms of freeing them, you would want to free from the GPU first to do an exit data and to delete it off of the GPU first, and then from the CPU. And the reason for that is inside not the compiler, but actually the runtime, the compiler has something they call the present table. And this keeps track of every pointer that has been moved onto the device. And it says, for this host pointer, coincides with this GPU pointer. And so if you did things in reverse, then this table would become invalid. You free your host pointer, and now there would be this GPU data living there forever that we have no access to. So it would leak that memory. Or again, if you did it the other way, if you can't really allocate on the GPU until the CPU data is there. So you do need to do it in that order. There was a question, and I believe this goes back to my example with the initialized vector. If I'll go back up to the code, update directive here says, why did I use an update directive here rather than just using a copy in after initialization? And it's a very simple answer of, this gives me an excuse to teach you how to use an update directive. And yes, someone could have implemented it differently with a copy in.
Jeff, can I jump in here?
Sure, go ahead, Matt.
So one of the questions that I've been doing is on basically deep copy. I wasn't too sure. Are you going to cover deep copy in another slide or another?
The extent of deep copy that I plan on discussing at all in this course is on this slide right here, where we copy in the structure of A followed by the array members.
Okay, perfect. So what I was going to point out, because there's a lot of one thing I would do is I actually wrote the chapter in the book on deep copy, on how to do manual deep copy. So if you get the book, chapter 5, kind of goes through code examples on exactly how to do this. The basic issue is that OpenACC will do a shallow copy currently. There are proposals on the board. Jeff can probably speak to those more on how to do a deep copy, but it's not part of the standard as of yet. So right now it's still a shallow copy. So if you have got a class or some other type of structure that has dynamic data members in it, such as a pointer or a Fortran, an allocatable type or something like that, what happens if you put that structure, like in this case A, in that copy in, it's going to copy just that structure. It's going to do a shallow copy, including the pointers. So if you're going from host to device, you're copying host pointers to the device, and you'll get an illegal address if you try to access that. So instead, you need to create the structure on the device. That's what this copy A is doing here. And then what happens is you create the individual arrays, or the objects that those point to. And the compiler does what's called an attach at this point. So it creates the actual data for that array, and then manually fills in the device pointer into that structure. So Jeff has it now. This is perfect. Then you can act on this device. But however, if you go in and change row offsets, or worse, if you come in and do a copy out of A, you're actually going to be copying out the device pointers. So you need to basically when you do the updates, you only want to do it on a fixed size or on the actual objects themselves. So if A had a couple scalars in there as well, you'd want to update the individual scalars and not A itself. So hopefully that's enough. If not, if you need more, we've got a whole chapter in the book on this. So.
Thanks for chiming in, Matt.
Sure.
A question I see here, someone asked is, is OpenACC friendly with NVIDIA Docker? And I can absolutely say yes. If you're not familiar with NVIDIA Docker, Docker is a way of running OS instances and specifically applications within a container in isolation. NVIDIA Docker takes Docker and exposes a GPU to these containers. And yes, you can run OpenACC applications inside of NVIDIA Docker. You would need to have either the executable built, or you would need to install your own licensed copy of OpenACC into Docker to build it. But yes, I've actually done this. It works beautifully. What's the difference between OpenACC, OpenCL? I saw another question very close to this, and CUDA. CUDA and OpenCL are very low-level languages where you are very explicit. I parallelize everything myself and manage the data movement myself and do all of this. So I have to write explicit kernels. OpenACC aims to do this at a higher level. If I'm a person with perhaps less knowledge of how to write parallel code, OpenACC allows me to maintain my source code, add directives, and the compiler handles parallelizing it for me. Please go back to last week's lecture for more information on this, but it is a directive-based language that handles this parallelism for me. It allows me to maintain one source code that runs across any platform, and it's capable of running both in parallel and in serial. So that's a few different questions. In a multi-GPU scenario, is there a way to move data from one GPU to another without first copying to the host? I need to double check whether this feature made OpenACC 2.5 or if it's pushed into the next specification. But we were looking at adding a library of API call that would allow you to say copy A on device 0 to A on device 2. We don't currently have a way to do that in directives, I don't believe, but that's something that we have looked at. It is a little bit challenging at the high level, but I think we did decide upon providing an API function to do that. Is there overhead on these allocate deallocate operations if we're using a GPU for the display? Sure, there's always some overhead when you're using the device for both display and compute. How much overhead? I don't have a measured value for that, but anytime that you're using the same device for both visualization and compute, they are going to be stealing resources of each other. And on NVIDIA GPUs, that does involve time slicing. So it's going to be every so often. It's going to be context switching between one operation and the other. Is there a way to write code that is portable across different architectures? And this is specifically moving from 3 GPUs to 4 or to 2. Come back next week. I have a very specific example where I've written a code that can run that speeds up on the computation on one CPU, but then because the way I encapsulate the data, I can actually easily ramp it from 1 GPU to 2 to 4, and I've run it as high as 8. So yes, I'll show a pattern next week on how to do that. Is it necessary to use PGI compiler for 4th applications or G4 when possible? GCC 6 and beyond does have support for OpenACC. It's not as mature as the PGI version, but it is available. To my knowledge, none of the distributions currently ship with the OpenACC-enabled version of GCC. So you would need to go and build it yourself. If you search online for GCC offloading wiki, there's a wiki article that explains how to build it, but you can use G4. You just have to jump through the extra hoop of enabling that support. Let's see if I can pick one more final question here before we go. How does the gang size get mapped to the SM? So let me go here real briefly for people who do have some CUDA background and want to try to translate this in your head. I do try to teach this without assuming CUDA knowledge. Gangs, we see here, these translate pretty nicely to CUDA thread blocks. And then workers and vectors you can think of as the dimensions of those thread blocks. And that's how you would translate them. And if you look at the compiler feedback, if I can find an example here, that the compiler actually tells you exactly that. So here it's saying the thread block index X is vector 32, and the index Y is 4, and then block index is the gang. So that's how you would map that. And I think we'll have to close the questions there. Continue to post questions, and we'll try to answer them in written form and post them for you.
Thanks, Jeff. I would probably, if you could, answer one more, because there are a lot of questions regarding the workers, gangs, vectors. People
Sure.
are still confused. If you can reiterate what the difference is, would be great.
Okay, sure. So workers, gangs, vectors. So vectors are the absolute tightest level of parallelism. When I operate on a vector, if we picture, let's say, a column in an Excel spreadsheet, I want to apply the same operation to every cell. I want to double the value of every cell. A vector operation would be taking it and saying, I'm doing the same operation, so I'm just going to apply it to all of them. I don't have to go one at a time and say, take this, add it together, store that into my cell, move to the next cell, add them together. I don't have to do that manually. Excel has a way to say, apply this operation to all of those. That is a vectorized operation, okay? So think of vector as all multiple data elements getting the same instruction applied to them. Now, workers are a way of saying, if I want to do vector operations, but I don't have enough work to do this. And so workers allow me to do multiple vectors. And so I can say, in the case of this code, then I really couldn't support more than a vector length of 32. So I'm going to use multiple workers and do 2 vectors of 32, or 4 vectors of 32 is what I've actually shown. Gangs. Gangs operate independently of each other. So if you take up your iterations of your loop and you break them across gangs, and again, if you're a CUDA programmer, this is a thread block. These gangs can operate in any order. They can operate in parallel. They can run in reverse order, in random order. It doesn't matter. They're completely independent of each other. And so this is my coarse grain of parallelism, where I break it up, and this on video hardware is what gets spread out across the hardware. So having a lot of gangs means I can run across the entire GPU, because it doesn't matter what order they run. All that matters is that at the end, the results have been completed. So gangs are the scalable parallelism that runs across the GPU. Vectors are the fine-grained parallelism that operate in a single instruction, multiple thread manner on the GPU. And workers are this in-between thing that allow us to operate multiple vectors. So I hope that was helpful. And if continue to post questions, and we'll try to get everybody clarified.
Great. Thanks a lot, Jeff. Okay, let's wrap it up. Thanks a lot for all the questions you submitted. And we know that we haven't answered quite a lot of them. So let us take some time after the lecture, and we'll try to post answers after. So the Q&A will be transcribed and posted on their course page together with all the slides and the video recording as well. So just go to the same link as where you registered for the course, and you will be able to access all the recordings out there. So next session is scheduled for Wednesday, November 9th, the same time, so it's 9 a.m. Pacific time. If you have questions before next Wednesday, so please don't forget that we have Stack Overflow, and we also have an OpenACC@nvidia.com email. We will be monitoring that email as well, so please send us your questions. And finally, we're also looking for your feedback right after this session. Once you close the window, you will see the survey. So please take your time to answer the questions and submit any comments or recommendations. So we are going through this feedback and trying to improve every single time we do that. And thanks again for all your time and all the questions. We really appreciate it. And see you next Wednesday. Thanks again.